Imagine a battery that doesn't rely on rare metals, lasts for years, and gets its power from how atoms talk to each other. That's not science fiction anymore. Scientists have just engineered a brand new kind of catalyst where two atoms, iron and cobalt, are stacked vertically and work as a team. And that tiny atomic change leads to a massive jump in battery performance. So what is this? How does it work? And why should anyone care? Let's break it down. First, what is this thing? At its core, this research is about zinc-air batteries. These batteries use oxygen from the air to generate electricity, which makes them lighter, cheaper, and potentially far more energy-dense than lithium-ion batteries. Zinc-air batteries have been around for a while, but they've had one big problem. The chemical reactions involving oxygen are slow and inefficient. Those reactions happen at something called a catalyst, which is basically the engine that makes the chemistry go faster. Traditionally, the best catalysts use expensive metals like platinum, iridium, or ruthenium. That works, but it doesn't scale, and it's not sustainable. This new research throws that old approach out. Instead of precious metals, the scientists used iron and cobalt, which are cheap and abundant. But the real breakthrough isn't the materials, it's how the atoms are arranged. Now here's where it gets cool. Most catalysts either use clusters of atoms or single isolated atoms. Single-atom catalysts are efficient, but they hit a performance ceiling because one atom can only do so much. These researchers asked a different question. What if two atoms could cooperate intentionally? Instead of placing iron and cobalt atoms next to each other on a flat surface, they stacked them vertically, one above the other, inside layered carbon materials like graphene. This creates what's called an axial dual-atom catalyst. In plain English, the atoms are lined up like a microscopic totem pole instead of lying flat. That vertical alignment lets their electron orbitals interact, something called d-orbital coupling. This changes how oxygen molecules bind, break apart, and release during battery operation. So how does it actually work? Inside a zinc-air battery, two reactions matter most. When the battery discharges, oxygen molecules grab electrons. This is the oxygen reduction reaction. When the battery charges, oxygen is released again. This is the oxygen evolution reaction. Both reactions are slow because oxygen bonds are strong and stubborn. In this new catalyst, iron does most of the heavy lifting, directly interacting with oxygen. Meanwhile, cobalt subtly reshapes iron's electronic structure, making those oxygen bonds just weak enough to break and reform quickly. Not too strong, not too weak, just right. This atomic teamwork lowers energy barriers, speeds up electron flow, and dramatically improves efficiency in both directions, charging and discharging. The scientists didn't just guess this either. They watched it happen in real time using advanced X-ray and Raman spectroscopy and confirmed it with quantum-level simulations. Now let's talk results, because this is where it really shines. When they built a zinc-air battery using this catalyst, the performance was stunning. The battery hit a peak power density of nearly 465 milliwatts per square centimeter, which is extremely high for zinc-air systems. Even more impressive, it ran for over 3,700 hours of continuous charge-discharge cycling without falling apart. That's months of operation. And it outperformed batteries using platinum-based catalysts while using cheaper, more sustainable materials. They even built flexible versions that could bend and still power sensors, LEDs, and small electronics. So why is this important? Because this isn't just a better battery, it's a new design philosophy. Instead of asking, what's the best material, scientists are now asking, how should atoms be arranged to work together? This approach could reshape grid-scale energy storage, backup power systems, wearable electronics, remote sensors, metal-air batteries for electric vehicles, and even fuel cells and hydrogen systems. Anywhere oxygen chemistry matters, this kind of catalyst design could matter too. And here's the really exciting part. This doesn't rely on some rare lab trick. The materials are scalable. The metals are abundant. The synthesis methods already exist in industry. So when will people actually see this? Short answer, not tomorrow, but sooner than most breakthroughs. In the near term, this kind of catalyst could appear in high-end zinc-air batteries for stationary energy storage, military or aerospace power systems, wearable and flexible electronics. In the midterm, think 5 to 10 years, It could help zinc-air batteries compete seriously with lithium-ion for large-scale storage, especially where safety and lifespan matter more than size. And long-term, this atomic pairing strategy could influence how catalysts are designed across clean energy technologies. The big takeaway? This research shows that small atomic changes can unlock massive performance gains, and that the future of energy might depend less on discovering new elements and more on mastering how atoms work together. Sometimes the biggest breakthroughs happen at the smallest scale. Check out more at newswade.com.